Okay, so we're going to be looking at module number 5, which is gear kinematic analysis and selection. This is going to be chapter 10 in our textbook, and you can kind of see things are kind of positioned the normal way. So our learning plan is going to be up here. That's where we have our PowerPoint presentation. This is just an extra little thing. It's some gear arrangements. Feel free to take a look at that if you want. The session recordings, I do have the session recordings out there from last year, but I haven't. I'll populate the ones that we do here. So those will be added after this evening. Then we have practice problems and assignment number 5. So there's quite a few practice problem examples because these are going to be examples that we end up doing from our textbook as we go through the lecture. You will be handing those in, okay, just like we have been. And then I do have 2 questions at the end. Make sure that you're answering these. I've had to give some zeros because you guys are forgetting them. So it is important. This time we're going to have 2 things that you learned in module 5. And then what I'd like you to do is to name and describe 3 places where you see applications of gears in your everyday life. So kind of keep your eyes open a little bit. And when you hand your practice problems in, share that with me. And then you're going to notice our assignment. Tonight, we're going to be getting through a lot of the material that you need to work on the assignment. So once we're kind of done here with our lecture portion, we're not going to get done with everything. We'll see which problems there that are assigned we'll be able to do. So let's take a look at our learning plan. And we're going to look at our first PowerPoint presentation, which is part 1. So I'm going to pull that up here. I'll zoom out a little bit. And we're going to be looking at chapter 10. Chapter 10 starts on page 260, okay? Now, just as we always have been in this particular class, you're probably going to notice that we don't hit and look at each and every section out of the chapter. The PowerPoint presentation will guide us through the places that are going to be important to us in order, that are going to apply to the things that you're assigned to do. So our objectives for this chapter are, number 1, identify different types of gears. We're going to be able to, by the time we're done, calculate center distances and physical, properties of gears, and then also calculate velocity ratios and trains. Now, as we look at gears, the function of a gear is to transmit rotational motion from one rotating shaft to another. Now, this can happen in either an increase, a decrease, or stay in the same. Additionally, we use gears sometimes to just simply change the direction of rotation, and we use it to increase or decrease torque. Okay, now in kinematic analysis, we will not be dealing with torque. We'll talk a little bit about forces and torque just to kind of set the background and just kind of understand some concepts, but we won't be calculating torques and forces. We're going to save that for design of machine elements. You guys are going to have that in the spring. And in that class, you're going to kind of finish up gear design. We're going to start here with just the kinematics, and we'll kind of see where that is. Velocity ratios, figuring out number of teeth, diametral pitch, pitch diameters, physical sizes, center distances, as we said. But then you're going to finish up the design by specifying the size of the tooth, the material that you're going to be using, maybe some heat treating if it's metal gears, and that'll be done in machine elements. Now, typically gears are going to be mounted to some sort of a power source that is going to be giving them, what we call the input motion or the driver motion. And many times that input has a very high speed, and we're looking to reduce it so that we not only reduce the speed so it's more usable, but also to increase the torque. If we look in our book, underneath our camera, looks like I gotta start my camera here. Give me just a second. Okay. On the first page of our chapter, down at the bottom here, kind of shows a nice little example of a simple gear drive. And this is a gear drive for a scanner or a printer. And you'll notice that there's an electric motor coming in. And attached to the shaft, on the end of that shaft, this is our first gear, okay? Now that gear is a smaller gear. This is going to be our higher speed gear. and it's called the pinion. And it's engaged with a larger gear. And when we have a set of gears that are in engagement, the smaller of the two is called the pinion. The larger of the two is called the gear. So the gear that's here is larger, but basically because it has more teeth around it. So a very typical problem that we're trying to solve, or a function that we're trying to achieve, is to slow that RPM down, engage it with a larger gear with more teeth on it, so that when this is rotating, this is going to have to rotate more revolutions than the larger one. So it slows down the operation there. Okay. Then the way that these two look, they look like they're the same size gear. In this case, they're going to be pulling paper through those rollers, as you can see. So this would not change speed. It would just change direction in terms of the motion that the gears are going to accomplish. So here's just like a very simple application of gears. Let's go back to our PowerPoint. Now, there's a number of different types of gears that we could study, and I wish we could spend more time and look at a couple different arrangements. We're going to be identifying the different types of gears that we see here, but we are going to be focusing on designing for spur gears. So let's go underneath. And we're going to look at the top of the next page, which is page 261. And we're going to see a couple different types of gear arrangements here. This isn't every single type of gear, but it's a lot of the most popular types. So the first one that we see is going to be the set of gears here. And this is a set of spur gears. Spur gears are going to be just teeth that are going to extend or be perpendicular, if you would, to the face width. The face width is going to be the thickness that we have on our gear where we have engagement with the teeth. They also are going to have a certain type of a tooth, which we will look at very, very soon. It's called an involute tooth profile, and it's the most common, most widely used type of gear. We are going to be focusing on those for that reason, but also the relationships that are developed are still going to cross over to the other gears. There's just going to be a little different nuances on calculations as you look at different sizes and calculating centers and things. The next type of gear arrangement here is a rack and pinion. And really what this is it's taking, if you would, the pinion on that gear, and it's taking the outside of a larger gear and kind of unwrapping it and laying it flat so that we go from rotational motion to linear motion. Okay, so it would pull that back and forth or run side to side along there, depending on the arrangement that's there. So our first kind of most common application is going to be where we're taking rotational motion and we're transmitting it from one rotating shaft to another. But we can also go from a rotating shaft into linear motion with a rack and pinion. The next type of gear arrangement here is an internal-external gear. So you're going to notice that the pinion, which is on the inside, the smaller of the two, is if you would, an external tooth gear, but then it's riding on the inside of the larger gear here. We won't be doing internal gears for our assignments. We're going to be focusing on external. So the next type that we have here is helical gears. Helical gears, you're going to notice if you look closely there, the tooth arrangement, the gear teeth are going diagonal across the face of the tooth. Okay, so if we compare it back to spur gears, the spur gears go straight across and the helicals go at an angle. Now, a couple advantages can be derived from that. Number one, because the teeth are at an angle, you actually have engagement on two teeth at any given time. One is coming in and the other one is leaving. So, so you end up having a quieter gear set because you don't have one clanking on the next, because spur gears are notorious for being kind of loud. So they're a quieter gear set first and foremost. Second of all, for the same face width, which is the thickness of the gear, you get more line contact to actually transmit your forces, motion, and torque through, which means that it can take higher loads as opposed to just having the length of the width of the face width. So, so it gives us more line contact that we can distribute loads over. So those are helical gears. And then herringbone is very similar. They're going to be very low profile teeth, but you're going to, if you might not be able to see it on my screen, but if you look closely in your book, you're going to kind of see the two teeth coming together. And again, they're going to be a quieter gear set, and they are going to, give the ability to transmit and distribute loads over longer lines, if you would. The next one that we have here, actually the next two are going to be bevel and miter gears. Those two, what they offer is really not so much a difference in rotational motion. It's going to be orientation. If we look up here, whether it's helical or the spur gears, that's called parallel shafting. And that's because the shafts are parallel to one another as they engage with the gears. Here, the bevel and the miter gears offer 90-degree orientation. So in some cases, that might be a benefit. So that's the big difference that they offer, as opposed to a standard spur gear parallel shafting. And then the last one that we have here is going to be a worm gear set. A worm gear has a spiral, and then it engages with, external teeth on a gear. What these offer is that they call it zero backlash. And we'll talk about backlash in a little bit, but what it ends up being is it's a more accurate, more precise positioning type of a gear set, so that when you reverse directions, you don't have any loss or gap in space as you go from one direction to the other. So those are kind of some basic gears, but like I said, we're going to be focusing on spur gears for the work that we're going to be doing in the relationships that we learn. So some gear terminology, okay, gear terminology. This is going to pertain a lot to, as we look at the involute tooth profile, what these things mean. So what I'm going to do is I'm going to go over underneath our camera, and we're going to look at the illustration on the bottom of page 262. This is figure 10.4. And what we have here is we have a close-up view of some gear teeth. And as we look here, the first thing I want to point out is this circle that goes right along here. Okay, this is called the pitch circle or the pitch diameter. That ends up being a very important circle on our gears, okay? It happens to be the place where when it engages with another gear, that's going to be the point of contact, okay? Now, above the pitch diameter is going to be what we call the addendum. Addendum is going to be from that pitch diameter or that pitch circle to the top of the tooth. The dedendum is going to be below that pitch diameter down to what we call the root of the tooth, which is right here. Okay, that's the root of the tooth, the bottom of the tooth. The dedendum will always be larger or taller, if you would, than the addendum. And that is because the addendum of the mating tooth is going to come down in, engage, and be down below the dedendum line of this tooth, for instance. I think couple pages, right here actually, on page 264, we see one tooth coming in to the other. They engage on their pitch diameters, okay? And then notice that the addendum is always going to, the addendum is never going to extend or touch the bottom or the root, the dedendum of the mating gear tooth. So by design, that dedendum is always going to be longer. The distance between the bottom of the root of one tooth to the top of the tooth of the other one engagement, this gap that's created is called the clearance, okay? And that's important to have clearance, obviously, because we don't want to have, gears that are going to interfere or bind with one another. Back a page. The next thing on here that I want you to be aware of is what we call the face width. The face width is going to be, if you would, the thickness of those gear teeth. The face width is going to be, since we have engagement on that pitch circle, this line right here, the thickness of the teeth, the face width, that's going to be where we distribute our forces over. The wider that face width is, the less stress those teeth are going to see. You're going to find out in machine elements that teeth are going to experience two types of stresses. Pitting stress, and that is going to be where it hits on one tooth to the other, like on the surface of the tooth. And then there's also going to be bending stresses that are going to occur. And all of those happen right at that pitch diameter, okay? Because that's where the point of engagement is. And then there's some other things on here. You've got tooth thickness. That's going to be the widest part of the tooth, or the part of the tooth that's going to be where we have the pitch diameter. I guess it's not quite the widest. The widest is at the bottom. These fillet radius is at the bottom. And, circular pitch is going to be a radial, not really a radial distance, but along the circumferential distance from one point on the pitch diameter to the very same point on the next tooth on the pitch diameter. That's another distance. Probably the two physical dimensions on here that we're going to hear the most about are going to be pitch diameter and face width. Okay, those are the two that you're going to experience the most. I see that there's a question there. Would that mean also smoother movement overall, or would it not notice when spinning? Oh, did I maybe miss this a little bit at higher speeds? Jason, I'm just going to ask what you were referring to. Oh, helical versus spur gears. Smoother movement, absolutely, because you are always engaged with the previous tooth before you touch the next one. On spur gears, on the other hand, you're not. You're kind of kind of pushing each tooth along independently. Yes, yes. So you do get smoother, quieter movement and motion with a helical. I always say helical. And then I come to find out, my husband said, I think it's helical. He goes, I always say helical. And then earlier today, when I had this class, Basic Mechanisms, I asked the class and they were all like, yeah, helical. And I'm like, shoots. But I'm not going to tell my husband I was wrong. I'm going to keep that. I'm like, I think I'm right. I think I might have been wrong. So now every time I say it, and then it doesn't sound right to me in my brain. Never admit it. I won't. Okay, let me go back over here. So we did pitch diameter. We did circular pitch, addendum, dedendum. We talked about clearance. And, we've got a couple more. So number of teeth. I think it's self-explanatory. Capital N is going to be the variable for that. And that is just simply counting how many teeth are on a gear. That's the number of teeth. Diametral pitch. Diametral pitch is the next subject that we're going to talk about. And if we turn the page and we go to page 263, at the very top, we have a illustration, and it's showing us standard tooth sizes, and this is pertaining to spur gear teeth. So you'll notice that we have the number 48 corresponding to the teeth directly above it. And then we have down here on the opposite spectrum, number 3 with a tooth above it. So what it's trying to say in this illustration is that when we have teeth that are engaged with one another, number 1, they have to be the same size tooth, okay? So these numbers represent what we call the diametral pitch, okay? The diametral pitch. So we had pitch diameter in the illustration earlier. That was the physical diameter of the gear at the point of engagement, okay? So pitch diameter is this diameter right here. That's the pitch circle, but if we would have the whole diameter going around, that would be the full pitch diameter. The diametral pitch is going to be the size of the tooth. When we have gears that are in engagement with one another, they have to have the same diametral pitch. So 10s will only be engaging with 10s. 6s will only engage with 6s, and so on, okay? So you have to know the diametral pitch in order to engage with another gear. Now, there is a relationship between diametral pitch, number of teeth, and pitch diameter. So by knowing any two of these variables, we can always find the third. Now, there are going to be a number of equations that we're going to be referencing throughout this chapter. So this is a good time to start an equation sheet, because it's always more convenient to have our equations all in one place instead of having to, kind of go through the chapter and try to find them, embedded within. So I am just going to start by saying gear equations. And what we'll do is we'll keep this handy throughout our lecture here, and we'll keep adding to it. So our first equation here is diametral pitch. So diametral pitch has the variable of capital P sub D, diametral pitch, is going to be equal to the number of teeth, capital N, divided by pitch diameter. So over here, we're going to list what each one of these are. So P sub D is diametral pitch. Okay. Capital N is number of teeth. And lowercase d is going to be pitch diameter. Now, units for each one of these. Units for each one. If we look at our equation for diametral pitch here, we can say that the units for diametral pitch are going to be teeth on top, because N is number of teeth, divided by pitch diameter, which would be inches, okay? So units for diametral pitch are going to be teeth per inch, okay? Teeth per inch. Units for teeth are going to be teeth, okay? And units for pitch diameter are going to be inch, okay? Are going to be inch. Always. I know, don't you? They're architectural students. Evidently they do. Maybe we have to start having more. Maybe more people would come to class if we would have more fun, huh? Is that what it is? I know. For those who come to class, it's yeah, next door they're having a good time. Sorry, this is school. We need to be serious. Very serious. Bring food. Okay, Christian, I'll start bringing more food in. All right. So this is our equation for diametral pitch. This relates those three items. And the big deal here is just getting used to diametral pitch and pitch diameter. It's what they're called, and that's it. Now, the other thing about diametral pitch I want to say is when we start doing our problems, diametral pitch will not be specified with any units. For instance, it'll say a number 5 gear. That's diametral pitch. That's a diametral pitch of 5. And it has the units of teeth per inch. You're never going to be given diametral pitch units, but in our problems, we're going to have to put them in there because we're going to need them so that we get the right units that are going to cancel out for items that we're going to be specifying. So for instance, if we go back to that illustration, here are standard tooth sizes. These are all diametral pitch numbers, but notice they don't have teeth per inch in back of any one of them. We just call it out as that's the number of the gear. Additionally, down here, diametral pitch sizes that are available, the standard sizes, notice it's not every size, okay? So for instance, we go 2, 3, 4, we don't have a 5, we don't have a 7, we don't have a 9, okay? Those are the standard diametral pitches. And again, their units are kind of left off of here because that's how we specify it. We say, and we usually say it's a number 5 gear, it's a number 10 gear, but it's diametral pitch. Okay, it's just kind of the way that it's specified. I am going to point out over on the right-hand side, the way that things are and the relationships that are that occur with, if you would, English gears are going to be the same for metric gears, except they have a different standard. So instead of diametral pitch, they use metric modules, okay? And these are their metric modules. Again, very similar, but different. We cannot mix. You can't do a conversion between metric gears and English gears. They do not mesh. You can't match them up, okay? So if you have a metric gear, it has to mate with a metric gear. If you have an English gear, it's got to mate with an English gear. There's not like a crossover there, okay? We will not be doing metrics again for the sake of time, okay? That's really what it is. We're going to focus and we're going to go deeper into spur gears, and then these same things cross over, but then you would just investigate if you need to do metrics at any time. The next thing on here that we haven't covered yet is going to be pressure angle. If we turn the page, pressure angle is going to be the angle that comes in, that's created, that the resultant force of the gear that's driving is going to be transmitting to the driven gear. So for instance, if we're coming in and our top gear is the driver and it's coming in, for instance, going counterclockwise, okay? That means that it's going to take its force and it's going to transmit it along this line as it comes in. And the line that's created is there are two circles on here called base circles for our gear teeth, okay? So the base circle on the upper gear to the base circle of the lower gear, if we take a line tangent through there, it's going to pass through the point of engagement at the pitch diameter, but that line is going to be tangent to the respective base circles. That angle of that tangent line there to the horizontal is going to be what we call the pressure angle. And that is the line that the resultant force is being transmitted from one tooth to the next. Okay, one tooth to the next. Now, there are three pressure angles. The first pressure angle here we see is 14.5. We do not design anything new to 14.5. Okay, only for replacement parts that are already out in the field. No new designs with 14.5, and I'll explain that in just a little bit. 20-degree is usually where we start everything. So 20-degree pressure angle, that would be for new designs. It's probably the most common among industrial applications. And then we have the 25-degree pressure angle, okay? Now, the difference between them. As we look at this angle coming in, and I'm gonna kind of go middle of the road with this one. Let's imagine that this angle right here is the 20 degrees, okay? The 20 degrees. So if I go along that line, for instance, and I show a resultant force coming in being transmitted. Yes, we are not going to be worrying about forces in this class, but let's say my resultant force is coming in, just for the sake of why is there three different angles. So this is a 20-degree. Now we know from statics that that angle coming in at 20 degrees is going to have a vertical component that's going to go down, and it's going to have a horizontal component that's going to go to the left. This one that's coming down is called the like force normal, and the one that's coming in perpendicular is going to be the force tangential. Okay, the tangential force and the normal force. You don't have to worry about this. We're not going to be calculating these, but I just think it's important for explaining these three pressure angles. So as we look here, if we start that at our 20 degrees, like I said, this would have a tangential force. This would have a normal force. Now, let's increase that pressure angle to 25 degrees for the same force. So that means that the same force is going to go up at an angle. I know it's maybe more than 5 degrees, but it's going to go like this, and it's going to stop about here. That means that the tangential force is going to get shorter. Do you see that? That means less magnitude of the force is going to come in tangentially, but more is going to be on the normal force, okay? This is reserved for applications, 25-degree pressure angle, where you have really large forces and torques that you're trying to push through, because what's happening here is you're sending more normal force down to the center of your gear where there's actual material, as opposed to you're putting then less tangential force on, which is going to cause this to bend over and for this to pit away on the surface, okay? So when we are anticipating larger, bigger, more robust applications, 25-degree pressure angle makes more sense, okay? Now, let's go in the opposite direction, 14.5. Why don't we design for those anymore? Well, if this angle gets shallower, look what happens. I increase my tangential force. My normal force gets less. When we increase that normal force, the two stresses that we see on failure on gear teeth are, number one, going to be the pitting on the surface. That's due to this hitting all the time. The second one is going to be the bending stress, bending that over or shearing off that tooth. When we have a 14.5 pressure angle, we're going to have more tangential force and more chances of failure. So they just stopped being, they're considered a standard for only designs that are already out there and you're replacing them. Okay, so if you have something where the gear teeth got old or whatever, and you're replacing a gear set and they're 14.5, replace it. But for any new designs, do not design to the 14.5 pressure angle, okay, for these reasons. We're not going to calculate any forces here, but when you get into machine design elements, you will be calculating tangential and normal forces and those pitting stresses and the bending stresses, because those are going to be the ones that are going to be causing failure. So you have to size your teeth appropriately, then pick the right material, and then decide how much, hardness, if it's metal, for instance, that you're going to be adding to it. So that's what my discussion on pressure angle, and we just discussed the forces just to kind of give that visual of what's happening with the components of that resultant force coming in on the pressure angle. Now, the other thing about pressure angle is that if you have two gears that are meshing, they have to have the same diametral pitch, as we just said, same size tooth, but they also have to have the same pressure angle. Okay, also have to have the same. So you can't put a 20 and a 25 together because they won't work. They won't work. So any two gears that are in mesh with one another have to have the same diametral pitch and have to have the same pitch diameter, or in the same pressure angle. So now I think on this list, I believe we covered everything. So we have been looking at the shape of the tooth. We'll look at it again in this illustration down here. I don't know if you really get much more from it than really just the profile that we've been looking at, but this is considered an involute tooth profile. Okay, so it's very common in gears, or in spur gears. It's the tooth profile for spur gears. So let's look at example 10.1, and we will do this problem together. So on page 266, okay, at the top, it says here, we have a 20-degree full depth involute spur gear tooth, or gear with 35 teeth, has a diametral pitch of 10, okay? So it tells us here you have a diametral pitch of 10, but notice that there are no units in back of 10. We know that there's units, and we'll add those in the problem. It wants us to determine the diameter of the pitch circle, which is the pitch diameter. Then it wants us to go ahead and it says, do the circular pitch and the base circle. We aren't going to do those things. Back in the day, before CAD systems can, that automatically generate the teeth on a gear, we used to have to manually calculate this stuff for our designs, but it's really no longer required. So we're going to stop short of those two because it's really not going to come in handy for the next steps that we would do in the design process anyway. So we will focus on just determining the pitch diameter. So using, if you would, our gear equations here, we only have one on our equation sheet right now, but what we're going to do is we are going to use our diametral pitch equation there and the relationship between the teeth and the diametral pitch to determine the diametral pitch. So we need to look up here and decide what are we given in this problem. So it already tells us that we have a diametral pitch of 10. So this is going to be our P sub D, right? And then it's telling us that the number of teeth is 35. So that's going to be N. Okay. So we have two of the three variables in that equation. So for this example, this is one that you're going to be doing for your practice problems. And we are going to be doing it in the format that I expect you to do for your homework. Okay. So first of all, I don't know why, but there are some people, more than one, that you're not labeling your problems for me. You just start writing and then it's like, make sure you tell me what problem it is, whether it's an example problem or an assignment problem. I just have a couple that I'm like, how come we're not numbering? I need to know that. Okay. So first thing you're going to do is you're going to put your example number. Then, as you know, we are always going to be identifying the equation in variable form first. Don't just start putting stuff in equations and adding and subtracting or multiplying and dividing. I know you're eager to get into it, but I need you to write out the equation first. So the equation that is relating these variables is going to be the diametral pitch equation. Diametral pitch is equal to N divided by D. Now, in this case, we are going to be determining, we need to find, oopsie, an N in there, find our diametral or our pitch diameter. Okay, so that means this is going to be our unknown variable. We need to find that. And we're given the diametral pitch and the number of teeth. So we're going to rearrange this to solve for our D. So that means we're going to multiply this up, and then to get rid of the diametral pitch, we're going to divide that on both sides. So it's going to be D is equal to N divided by diametral pitch, right? Okay. Then what we're going to do is at this point, we will put in our numbers with the units, our numbers with the units. So we know that our number of teeth from the problem above is 35 teeth. So 35, and make sure you put teeth in back of it. Divided by a diametral pitch of 10. Now, as I told you earlier, when we're given diametral pitch, or even if we give a diametral pitch, it's not going to have any units, okay, specified. But there are units. Remember, back here, to calculate diametral pitch, it's the number of teeth divided by the pitch diameter. So it's teeth per inch. So we are going to write those units in the problem, okay? Because when we're looking for a pitch diameter, that's a distance. We're expecting units of inches in this case. If we don't put teeth per inch here, your units that you have are just teeth. It's not right. And then if you put D is equal to 3.5 inches, it's like they magically appeared. That's not how we do things. So you have to put teeth per inch in for the pitch diameter whenever you're using it, so that your teeth cancel, and now you're left with the correct units. Notice that we have inches in the denominator of the denominator. If you recall from algebra, that's like a multiplication in the numerator. Do you remember that? Maybe. So when inches are here, I like to say they multiply on top. Meaning, it's kind of like if you divide 1 by 1/2, okay? If you go on your calculator and you divide 1 by 1/2, what do you get? No. Do it. Do it on your calculator. What was that? Well, it's kind of like what we have here. The 1 will cancel and the 2 will multiply up. So if you divide 1 divided by 0.5 on your calculator, what do you get? You get 2, okay? So the units here act the same way. If I'm in the denominator of the denominator, it's multiplying on top. So my units are inches. So make sure that when you have diametral pitch that you always expand those out inside, okay? Even, they're not going to be given to you. I'm going to tell you, they're not going to be given. So you have to put them in. So our diameter here then is going to be 35 divided by 10. So that's 3.5 inches. Now, when you specify a final answer, you need to put your box around it, and you need to put the variable in. So if it's asking me for a pitch diameter, the standard variable for pitch diameter is D. You're going to say D is equal to 3.5. You are not just going to put 3.5 with a box around it. Tell me what you're solving for here. Go back to the question and give me an answer, okay? So that's our first problem. Remember, this is a practice problem, so you will be handing this in, making sure that you show that format. Again, this will be the format that I expect on the homework as well. Any questions on that example? All right. So good. Standard gears. So if we go a little bit lower on that very same page, there is a chart. And this chart gives us the standard equations for each one of the characteristics, if you would, on an involute tooth. Now, the American Gear Manufacturing Association is the, if you would, governing body or the standards body for gears. Okay, so they are the ones that come up with these relationships. Notice that to calculate an addendum, you are going to use the diametral pitch. To calculate the dedendum, you're going to use the diametral pitch. All of these characteristics are based on the diametral pitch, which is the number of the tooth, which is the size of the tooth. Okay, so if you ever did want to go back to that illustration earlier and calculate all of these items and generate manually an involute tooth profile, here are your equations. Okay, you don't need to do that because modern CAD systems, 3D parametrics have toolboxes and things like that that we can specify our gears out of. So we don't need to rely on that, but that is there. But I think it's also good to know that there is a governing or a standards body that oversees gears, just like there is for, you know, standard fasteners and things like that. Now, relationships of gears in mesh. And what we're most interested in, especially when we're talking gear kinematics, is how much space is this going to take up? So we need to know what is the center distance between gears. So I'm going to actually peek over at page 273. And down here, this is figure 1012. What this shows, I think it's nice to see like two full gears, and you can see where they're meshing with one another, where we have the teeth drawn. So as we saw earlier, this circle right here would be the pitch diameter. So notice that this is diameter 2, this is diameter 1. So this would be the pitch diameter of the pinion, the pitch diameter of the gear. Pinion, again, is going to be the smaller of the two gears that are in engagement, okay? Now, the other distance here is the center distance, and the center distance is simply the distance from the center of the pinion to the distance to the center of the gear. And remember that we are going to have engagement at the pitch diameter. Essentially, what's happening here is this pitch diameter is tangent to this pitch diameter, okay? So the center distance then becomes the radius of the pitch diameters added together. Does that make sense? Okay, so there are a couple equations at the top of page 268. This is equation 10.7 and 10.8. 10.7 is looking at just adding together those two radiuses that we just talked about, the radius of one gear plus the radius of the other, which we could also get by adding the two pitch diameters together and just dividing by 2. Or because of this relationship right here with the diametral pitch and the number of teeth, we can substitute and use the number of teeth and the diametral pitch as well. So what I want you to do on your equation sheet, add these two variations of your center distance, okay? I'm going to add them to mine. Now, something they don't do is they don't put the units in and what each one of the variables means. So I do want to add that on our equation sheet. So first of all, I'm going to take this book out from underneath. C is going to be equal to center distance. Okay, and that's going to have units of inches as well. Okay. R is going to be equal to the radius of the pitch diameter. That is also going to have units of inches. So it's not radians, it's radius. And then we already know that N is equal to number of teeth. We already know that D is equal to pitch diameter, and that diametral pitch, P sub D, is diametral pitch. So we don't need to add those variables, okay? So depending on the information that you have in a problem, you know, one of these, if you would, 3 versions of the center distance, you know, is going to work. It's going to work. So as we look back at our PowerPoint presentation, let's do example 10.3, which is going to be determining center distance, okay? Do a little bit of erasing here. All right, so in this problem, we have a construction site cement mixer. The gear transmits power from a small engine, okay? So notice we have these 2 gears in engagement. So here's our small engine, and off of the shaft of that small engine is going to be a gear. This is the smaller of the 2 gears that are in engagement. So this is going to be our pinion, and this one is going to be our gear, okay? This machine is shown, the pinion has 15 teeth and the gear has 30 teeth. Determine the center distance, okay? Determine the center distance. Now, oh, I forgot about this. It just said we have two 5-pitch, 20-degree, full depth gears, okay? So let's do this example. Okay, so this is going to be example 10.3. Okay. And as we look at our problem, first statement here, 2 5-pitch. Which variable are they referring to there? We have pitch diameter and we have diametral pitch. Which one do you think that is? It is the diametral pitch. Okay, your clue is this. There are no units in back of it. It's just saying a 5-pitch gear. Okay, so diametral pitch there is number 5. So we know for this problem, diametral pitch, capital P sub D is equal to 5. Okay, and we know that the units are going to be teeth per inch. They aren't given, but we know those to be the case. And that will come in handy for what we needed to do. The 20 degrees, that's the pressure angle. That is not going to be used in any of the equations that we have, but it's always good information because whenever we specify gears that are going to mate with one another, in this case, we've got 2 of them, they have to have the same pressure angle. Then the next thing here, it says the pinion has 15 teeth. What is the variable that we would call for the number of teeth? Do you remember? Capital N, yes. And since this is the pinion, we're going to call that N1. 1 is always the pinion. What was that? No. I wouldn't advise it. You're going to see 1s and 2s. 1 is going to be your pinion. 2 is going to be your gear, or yeah, your gear. So that's how you're going to see it most often. P and G. Could you do that? Yeah. Yeah. As long as you're consistent. Yeah. 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 So this is going to be 15 teeth. 15 teeth. Then as we look at our problem, the next one, it says that the gear has 30 teeth. So that one is going to be N2 is going to be 30 teeth. Okay. And we want to find our center distance. Okay. We want to find our center distance. Okay. Now, instead of having to page back, I know it's just above, but we've got a couple options for our center distance, right? We've got radiuses, we've got diameters, we've got number of teeth, we've got diametral pitch. Which equation here, based on the information that we have, which one would probably be the most efficient one to use? What was that? The second one, right? Or yeah, the bottom one here. So the number of teeth in 1 plus 2 divided by 2 times the diametral pitch. Yes, because we are given number of teeth and the diametral pitch. So it makes sense to use that one. So we're going to use the equation C is equal to N1 plus N2 divided by 2 diametral pitch. Okay. So we're going to put our variables in here. So this is going to be 15 teeth. Remember, you have to have your units with each item. 15, and this is going to be 30 teeth divided by 2 times our diametral pitch is 5, and the units here are teeth per inch. Okay, you have to put those units in for the diametral pitch. If you don't, you're not going to end up with inches as your units. So here, when we combine these two, this is going to be 45 teeth on the top. So teeth are going to cancel out, top and bottom. And then inches are in the denominator of the denominator. So they're multiplying on top. So our units will be inches. So we've got 45 divided by 10. Is it 4.5? Okay, good. Yep, 4.5 inches. Okay, C is equal to. Now, in the example in the book, they go through and they calculate the diameters for each, and then they divide by 2. And when they have this equation directly. So they do it two ways. You don't have to do it two ways. All right, just find the one that makes the most sense with what you have. And this one's direct. Okay, so any questions on that? So again, equation in variable form first. I always look for this. All right. If you don't have it, you lose like 3 points. That's a big deal to me. Okay. And by this time, you are second year, you have had me often enough. That's a requirement. Then I'm also looking for your units in every phase of the problem, canceled and or combined. In this case, they're canceled. Okay. Don't write teeth all over and then don't cancel them out, because I want to know what units are left over. Again, this is your assurance on how things are set up correctly. If you don't end up, if you don't put the teeth per inch here, you're going to end up with teeth as units for a center distance. That's not correct. Then you should be looking and finding out, like, what am I missing here? What did I do wrong? And in this case, it would be adding in the units on the bottom would be missing, and then you would have it right. So the number can come out, but I don't want units to magically appear at the end. Okay. All right. So that is example 10.3. Okay, so now we're going to go to section 10.7. I think that we're skipping a little bit here. We are. And 10.7 is going to start on page 273. Okay, 273. Now, spur gear kinematics. Spur gear kinematics is looking at what is the velocity ratio between two gears. So when I have a pair of gears that are going to be in engagement, each of them is going to have an angular speed, okay? That's going to be our W. And when we take the angular speed of the driver, which most often is going to be the faster moving gear, meaning it's coming off of a motor or an engine, divided by the driven gear, we are going to get a number or a ratio. Sometimes it's referred to as what is the gear ratio, or just what is the ratio between those two gears. And what it tells us is how many times the faster moving pinion has to rotate in order to get the slower moving gear to rotate once. Okay. So if we look back at page 268, and we look at that cement mixer, okay? What I want to know when I have the velocity ratio between these two gears is how many times does that little one have to go around to get this one to go around just once, okay? All right. Now, there's a couple ways we can determine that, okay? We can determine that right up here at the top of page 274. Okay, it's equation 1019. We can determine it by comparing the velocity ratios between the number 1, which is the pinion, divided by the number 2, which is the gear, which is also equal to comparing the physical radiuses of the pitch diameters of each, where we would put the gear radius on top or divided by the pinion radius on the bottom. Or we can compare the diameters of the pinion, or I'm sorry, of the gear divided by the pinion. Or we can simply count the number of teeth on the gear to the pinion. So remember, gear is 2, pinion is 1 in each one of these. So guess what we're adding to our equation sheet? We're adding the velocity ratio stuff here, okay? So velocity ratio is going to be equal to W1 divided by W2. Radius 2 divided by radius 1. Pitch diameter 2 divided by pitch diameter 1. And number of teeth 2 divided by number of teeth 1. Now, something I want you to notice is that the number 1 is only on top for the angular velocity, okay, for the W's here. And it's on the top because that's when it has the larger number, meaning it's going at a higher speed. So for instance, off of a motor, you can have 1750 RPM, 900 RPM, 1100 RPM, 1200 RPM. That your larger number is going to be on top. But then when we look at the physical size of the gear compared to the pinion, Now the gear gets bigger in all of these categories, and we want to put that value on top. Okay, so let's look here. W is equal to angular velocity. Now, the units are most often going to be given to us in RPMs, but we also know that we see this in radians per second. And we use it in and out of equations, which we'll see in just a little bit. And V is equal to velocity ratio. Now, units for velocity ratio. Look at the equation. What do you think the units are? I'm going to ask the virtuals. We haven't had much engagement lately with the virtuals. What are our units for velocity ratio, do you think? So look over here.
There shouldn't be any because it's a ratio.
Correct, Christian. Thank you. Yes, it wouldn't be any at all. They're unitless because when we're comparing the angular velocity on top, it's going to have the same units on the bottom. They're going to cancel. So it's going to be a number. Now, you have probably heard gear ratios expressed in 2-to-1, 3-to-1. What that means is, as I said earlier, how many times does that pinion have to go around in order to get that gear to go around once? So when we say 3-to-1, that means that the pinion has to go around 3 times in order to get the gear to go around once. Now, it doesn't have to be an integer number. You can have, decimal places in your ratio. That is totally fine. It might not come out even unless you have numbers that are divisible. So don't think that you're doing something wrong if this ratio isn't an integer number. It's okay. All right. Let's go back over here. The other thing that we see here is pitch line speed. Pitch line speed. I don't know why. I think I made this mistake. This is supposed to be VT, not VP. Pitch line speed is the tangential velocity straight line of a rotating element. Okay, so this is going to look familiar to us. If we look at the previous page right here on page 273. Okay, page 273 here. When we have these two gears that are in engagement, okay, they're going to be tangent at that pitch diameter. And this is also where forces are being transmitted. But additionally, the motion is being transferred here, okay, from the driver to the driven, okay? Now, what I want to show here is, imagine the center of the gear, the center of rotation. Let's say that that is the frame, okay? That's not going to move. And a lot of times it doesn't. If you remember some of the kinematic diagrams that we did that had like a circular element here, like a flywheel, we would go from its center of rotation and we would just draw it as a link to where it would connect. Well, in this case, might not physically be a pin that connects them, but we have connection between those two as they rotate. So this is going to be, if you would, link number 2. Okay, so link number 1 would be our frame. Link number 2 would be the radius to the tangent point on the pitch diameter. Okay, and now as this rotates, in this case for the gear, as this rotates counterclockwise, the straight line velocity component out here at the radius is going to go straight down, perpendicular to the radius back to rotation. Do you see that? Does that look familiar to you from our other kinematic diagrams? Yeah, we've seen this a number of times. This is, if you would, velocity B. If this is point A, this is point B on our 4-bar mechanisms, this would be the velocity, the straight line velocity at point B. Except now we're looking at it in terms of the radius on a gear. Okay, so the relationship that we developed back in module 3 between rotational velocity or angular velocity, straight line velocity, and radius, the same equation that we're going to see here. So if we go to the top of 274. Look at that. Now, the key here is when you find that straight line velocity, you probably will be dealing with a pair of gears. Make sure that you pair your radius with the same angular velocity. Meaning, if you're using the radius on the pinion, then you have to use the angular velocity of the pinion. Don't accidentally put in the angular velocity of the gear. Okay, so you got to kind of keep those straight and make sure that they're labeled appropriately, right? So we can add this equation as well to our equation sheet. So here, we can say that the tangential velocity or the pitch line speed, okay? Because it's the speed along the pitch diameter. That's why it's called pitch line speed. It's going to be equal to radius times angular velocity. Now, in this equation, remember this, well, I should put it right in back of it actually. Our units are going to be inches times radians per second, okay? So these units for our angular velocity have to be radians per second in this equation, just like they were in our previous modules, okay? So VT is equal to pitch line speed. And as we combine these two, these units are going to be inches per second, right? Inches per second. So that's a reapplication of something that we've already looked at. Okay, something we've already looked at. All right. I think probably ready to another example. Okay, so example 10.8. Example 10.8. Right, my paper's in order here. Let me go underneath. The example that we're going to look at is example problem 10.8. And here we have a set of gears is used to reduce the speed of an electric motor to a shaft driving a grocery checkout conveyor. The gear on the motor shaft is a 10 pitch pinion. That's going to be our diametral pitch, right? It has 15 teeth, so that's going to be the number of teeth on our pinion, okay? And it drives at 1800 RPM. So that's the motor. So they have it all kind of labeled down here as well. W1 is 1800, N1 is 15 teeth. And it's rotating clockwise. Determine the speed of the mating gear. That's going to be W2. Okay, so this is going to be W2. We want to find what that is. When the mating gear has 45 teeth. And then it also wants us to calculate the pitch line speed. So that's going to be VT. Okay, we have to do VT as well. So W2 and VT. Let's start our problem by identifying what we know and what we need to find. So go ahead and write, based on that example, what you believe you know, identifying the standard variable with any units that you're given, and then what you have to find. So known and unknown this time. I'll give you a second to write down from that problem what you believe. So known, what do we know in our problem? What do we know? Diametral pitch. So diametral pitch is what? 10, okay? Are there any units? There's none given, but are there units? What are they? Teeth per inch, yeah. So go ahead and put them up there just because you're going to be needing them in your problem. Okay, what else do we know? What else do we know? What was that? Okay, so that's going to be N what? 1 or 2? N1, and what is that? How many? 15 teeth. Okay, what else do we know? James gave us 2. We know the angular velocity of the first gear, so W1, and what is its value? 1800 RPM. Excellent. All right, what else do we know? Which one? Number of teeth on the second gear, and how many are on that one? 45 teeth. Okay, do we know anything else? I think that's it, right? Virtuals, what is unknown? Excuse me. What is unknown? W2, yes, W2, we need to find that, right? So that's going to be the angular velocity of our gear. Excellent. And there's one other thing that's unknown. What is the other thing that we have to find? Anyone? James? Yep, the pitch line speed, right? VT. Okay, those are the 2 things that we have to find. All right. So if we look at our equation sheet, we're probably going to look, okay, where are W's and T's, and what do we need for them? So you will notice that we have an equation with a W and a T in it, but unfortunately, we would have 2 unknowns in one equation. But that would just mean that we probably have to solve for one before the other and then plug it in, right? So this is probably an option for us. But we also see W up here, don't we? See W up here. So with the information that we have, we know some numbers of teeth. We know one of the W's, and we need to find the other. So here in the velocity ratio relationship, okay, we can set these 2 equal to these 2. You see that? And we would know 3 of the 4, which we would only have one unknown. So the W2 then would be our unknown. Then once we know W2, we can then use the second equation to solve for the pitch line speed. So what we're going to do is we're going to do exactly that. So our step number 1 is here is going to use that relationship that we just saw, W1 over W2. It's going to be equal to N2 divided by N1. You have to get these right. Remember, in this relationship here, the 1 is on top on only the angular velocities. It is 2's on top for the rest of them. So don't accidentally put N1 on top here to match up with the W1. That's not how it is. So solving for W2, that means I'm going to have to multiply it up over here and then get it by itself. So I'm going to rearrange. I'm going to multiply W2 here. So that means to get W2 by itself, I'm going to multiply both sides by N1. So N1 is going to go on top. I'm going to kind of sneak that in there. I'm going to rewrite this. And then N2 is going to go on the bottom down here. So my equation is actually going to be W2 is equal to N1 times W1 divided by N2. Doing our algebra. Does that make sense to everybody? Everybody get that? Same rearrangement? Now that I have my W2 solved for, because that's what I've got to find, right? Now I can put my values in here. So I'm going to put my number of teeth for 1, which is going to be 15 teeth, times W1, which is 1800 RPMs. Now in this equation, we can leave the RPMs. We'll see why in just a little bit. We don't have to convert it. Divided by N2, which is 45 teeth, okay? Now here we want to cancel out the teeth. Don't just leave the teeth there. The whole purpose of carrying the units along is to cancel out and make sure that we end up with appropriate units for the variable that we're solving for. In this case, we're solving for an angular velocity and RPMs is left over. That is good. So what do we get for our W2? Is it 600? 600 revolutions per minute. Okay. Box around your final answer, identifying that it's W2 is equal to. Do not do a string and then have the answer over here and put a box around it. Label it with the variable that it is. Answer the question. It wanted to know, what is the angular velocity of the second, or the gear, right? The larger of the two there. All right, so now that we have our angular velocity 2, we should be able to find the straight line or the pitch line velocity, and that's going to be this equation. So number 2 is going to be VT is equal to R times W. Now this is where we want to pick. Do we want to use W1 or W2? It doesn't really matter, okay? So in this case, W1 was a given variable. It's always good to try to use as much original information as possible. In the event we calculated W2 wrong, now all of a sudden we're then going to, induce that error in the next part. So we're going to take the angular velocity of the pinion, which means that we have to use the radius of the pinion. You cannot mix and match 2s and 1s here, okay? As we said earlier. You'll see whether you use the pinion or the gear information. So if you would say R2 times W2, you're going to get the very same answer as you would using R1 and W1, okay? So we know what W1 is. It's 1800 RPMs, but we weren't given a radius. Can we calculate a radius? We can. We can calculate our diameter and divide by 2, right? So using the diametral pitch and the number of teeth on the pinion, we're going to calculate that pitch diameter. So we need to do that work. D is equal to, it's going to be N divided by our diametral pitch, and this is going to be 1s, okay? So the number of teeth on our pinion is going to be 15 teeth. The number or the diametral pitch is going to be 10. But remember, you have to add the units, teeth per inch. Teeth cancel out, inches is going to multiply up. And D1 should be 1.5 inches, okay? This is what we're not going to use. We're not going to use 1.5 in our equation. What are we going to do? R1 is going to be equal to D1 divided by 2. So 1.5 inches divided by 2. R1 is equal to 0.75 inches. That's what we're going to use up here. Okay. So 0.75 inches times 1800 RPMs. What do we get? You get the wrong answer. Nope, that's wrong. Did you multiply 1800 times 0.75? What's wrong with that?
We need to switch it to radians, right?
Yes, we do. And this was on purpose. I did this on purpose. We need to switch. Remember, and we put it on here. Our W has to be in radians per second. Okay? Don't forget, in and out of that equation relating the straight line velocity and the radius. So we didn't convert that yet, so we need to convert that. So we need to take 1800 revolutions per minute, and we need to convert that to radians per second. So go ahead and do that. Let me know when you get an answer. 188.49 radians per second, right? That's what we're going to use up here. 188.49 radians per second. Okay. That's why you have to watch your units. If you put the 1300 in there, or I'm sorry, the 1800 in there, and you had RPMs, and if you recall, our pitch line speed needs to be in inches per second. You weren't getting anything close to that, okay? And if you snuck those units in, you weren't paying attention, okay? What do we get for our pitch line speed? 141.37 inches per second, because it's inches times radians per second. Radians magically disappear. There it is. William, thank you. Yes, very close. You probably had a little bit of a rounding in, one of those couple areas. Awesome. All right. Questions? They're kind of fun. Aren't you looking forward to doing these problems? I'm happy for you. I'm excited for you. All right. Right now is a good time to take a break. I've been talking for about an hour and 20 minutes. When we come back, we will resume where we left off. So it is, let me just stop our recording here.